Greetings 2021ers, this is Professor Kaufman, and this video will survey what's involved with Project 3 and help you get started on it. The project itself deals with assembly coding and debugging, and many past students have found it to be a particularly challenging project. Thus, we're giving you a couple weeks to work on it, and we'll provide various support activities in the form of labs and homeworks that cover similar techniques to what you'll need to use in the project. Hopefully this overview video will help you get off the ground and running. Fortunately, the domain for both problems involved in the project will be familiar to you because they're similar to what was done in Project 2. The first problem will recode what you did in the battery meter functions in C, but recode it down at the assembly level, which will take some care. The second problem will be a debugging exercise in the same vein as Puzzlebox was in Project 2, although this time you'll be given, instead of source code, a binary file, and we'll need to debug it at the assembly level. And we'll look at a few tricks for how to do so in this video. Let's start with the first thing you should always do, which is to download the code pack associated with the project. Here I will grab the link associated with this thing. I could sort of do a save as and so forth, but I'm feeling command liney today. And so I'll open up a shell over here and use wget. Paste in that link that was on there, and wget is a handy little utility that will download things from the internet in a terminal for you. Assuming that this thing downloads properly. There it is. And then I should, in this directory, have this p3 code.zip. I'll run the unzip command on that, and that should create my little p3 code directory here. When I pull up a little directory browser, you can see it's here, and we have a bunch of files in here. Notably, you have similar files to what you'll have seen in Project 2, where there's a bat.h, bat.main, and bat.sim, but no source file for the required functions for things like bat update or set bat from ports and so forth. One thing that you might do immediately is to copy over your C file from Project 2 into this directory. And this will serve then as a way that you might go about sort of getting a sense of what's happening. And that C file should pass all of the tests out of the gate, assuming you completed Project 2. And eventually then you're going to have to create an assembly version of all of the three functions that are in there. Now we acknowledge that not everyone had a chance to complete Project 2, and you may have some doubts about your solution, even though perhaps you passed all tests. Getting a succinct and good plan in the form of C code for your bat update file, that is something that is important because starting from a good sort of plan of action is the best way to find success at assembly. If you have a meandering path, sort of long-winded code in C, trying to convert that to assembly can be difficult. So there is a special provision in this project that as you would not have completed Project 2 or want access to the instructor solution for it, visit an office hours and state as much to the folks that are there. They'll be happy to walk through your solution in C to those assembly or those functions, and then provide for you the instructor bat update.c file, which can serve as a reference and a good starting point as you code assembly. But you'll see up in the project, but this must be done in person during office hours. Not necessarily in person like you have to visit there, but you can't just email a TA and send, yo, bro, send me the solution. They're not going to fly for that. Instead, you actually have to spend some time to walk through that with them during an office hours, either in person or online. The file that we're going to create that has all the functions in it is called bat_update_asm.s, and this follows the convention I laid out in class that I'll name most of the hand-coded assembly _asm, as if you were to generate assembly through GCC from bat_update.c, it would be called bat_update.s. So the little suffix here of asm serves that. Let me actually create that file now. I'll do so in my Emacsy way over here, but you might sort of make a new file over here. It is empty, and my particular editor has this in assembler mode. You do well if you're using, for instance, VS Code to install an extension that syntax highlights for assembly. There'll be links to that posted in various spots, including Lab 7 this week. A short video of how to do that at any rate. So then, the first thing you'll probably want to do along these lines, after maybe doing a little bit of reading, is to find the template that's provided for this, which is here. It's in this section marked Structure of BAT Update ASM.S. Now this lays out the three main parts for the three functions that are to be used. And a good spot to start in terms of getting underway is to copy this thing and then make some changes to it so that we can actually compile this thing. So I'll copy this entire little outline over here, and then I'll paste it in over here, and you can see it's syntax highlighted. Now it's worthwhile just to survey this thing as a sort of outline. As we discussed in lecture, assembly code is primarily comprised of text portions, thus the little text directive up here, sometimes also stated as a .section .text, but abbreviated .text over here. And that is usually populated with functions and function names and so forth. So for instance, the first function I have to write, set bat from ports, that's stated as a global up here so that it can be accessible outside of it. And then later on down here, you see a text portion that is a set display from bat and a global update, or sorry, a global for bat updates, another label for that down here. Those are the three functions that must be written over here. Assembly files can also have a data portion, which is where global variables of one sort or another can be declared. And you'll see that here, where I've declared my int and other int and a short array over here. You'll find that in the second function, it's tremendously useful to have a short little array of bit patterns, for instance, my array over here, or I could instead call it bit patterns. And then make use of that in various ways. For instance, I could put a 0b001101 for some reason in there, and a bint 0b011101, something like that. That should ring bells for you if you completed project 2. It's useful. And then you might reference bit patterns as a global variable. But right now, what I want to do is to get this thing set up so that we can actually compile it and run it with tests. To that end, there's some things in here that don't really work. For instance, there's example syntax here with this move x. If you follow on the lecture, you'll know that there is no move x. There's got to be a move l or a move q or something like that. But this is a useful bit of syntax to be aware of, that if you have a global variable, then you can copy its value from the global variable into a register using this approximate syntax. And in the first function, you will definitely have that case. For right now, I'm just going to leave this as note. I will comment it out by popping down a little hash here. Doesn't really want to do that, so I'll use the Emacs syntax for it. Let's see. Oh gosh, I put it in read only. Well, that's not good. Okay, here's what we're going to do. We're going to kill this thing, yeah, and recreate it. There we go. Okay, so good. And then I want to comment this thing out for now because I went there. Set bat from ports really only needs to have a return statement in it in order to be sort of workable. And to that end, then I'll just put down here a ret instruction. Say when you get to here, just return from it. And that's all that's needed in this case to have a sort of running assembly function. It's not going to do anything. It's going to fail tests, but hey, at least it'll compile and be runnable in that respect. I'll do the same thing for these others over here. For instance, this bit of syntax is useful, but I don't really want to look at it right now, so I'll put a ret down here, and then down here a ret as well for this thing. Okay, so I think with that in place, if I jump over here, I have now this bat update asm.s. I should be able to type make, and this thing will compile the bat main. And if I run it, bat main, it'll require a couple parameters that indicate what the voltage sensor should read. So let me just put like a 5,000 maybe. No, maybe something a little bit of that, like 6600 or something like that. And we'll say in volts over here. And if I get nothing like on display, but hey, the main program compiled and it ran, so that's good. And if I do a make test prob 1, then yeah, so the tests are going to run right now, and I get a bunch of failures, but those are things to sort out. All right, and inside of 5 minutes here, we've already got like sort of my basic setup for problem 1 going. Now, what comes next is to start looking at how to fill in definitions for these functions. And commenting here is potentially useful. For instance, within this set bat from ports, you'll want to review the documentation associated with that function. It is listed in several spots, including over here in the spec in a section on that function itself. The original documentation, what came from the C version, is over here, and it's good to sort of read that. It'll remind you, for instance, that, oh, you've actually got to look at some global variables to get this function correct. And lo and behold, there's some benevolent person who mentioned this is how you access global variables in assembly, just for an occasion such as this. There's also reminders of some of the structs that are at stake. For instance, within this function, the C prototype reveals that it takes one argument and that that argument is a pointer to a struct. You'll notice that assembly lacks any such features. And so it might not be a bad idea to write yourself a few notes about things. For instance, here I might note takes one argument, pointer to a bat t. And then you might look up, okay, I'm trying to remember, there was something about registers and arguments for functions in assembly. I think, yeah, there's like, some special register that is supposed to, be for arguments. And at that stage, you might look up, a handy dandy diagram that reveals, oh yeah, argument 1 for functions comes in the DI family register. And if it's a pointer, it'll be 64 value, so RDI. So over here, I'll make a RDI is a pointer. So something like that. And so I might do something right away with RDI here, or later on do something with RDI. And it's good to remind then that, oh, what I'm supposed to do with that is actually to set the fields of this bat based on global variables that I pull out. So eventually there'll be some like, oh, moving things to various spots. In addition to that, there's some demonstration syntax that's down here that's a little closer to what you might want, along with some demonstration syntax about movements as you would want to move some piece of data to this field. If there was a pointer stored in this reg over here to where this bat was at, then this movement here would populate the millivolts field, this one would populate the percent field, and so forth. And again, struct fields, just as you would have a pointer that there's some offsets, like 2 bytes or 0 bytes or 3 bytes away from where the start of the struct is at that those fields go to. Now your strategy is going to be a little bit different in the second function, the set display from bat, because rather than a pointer to a struct, you have an actual struct over here. And for this, you'll need to know something about how structs are packed into registers, so-called packed struct formatting. And in that case, the entirety of this bat is going to be in a single register, the RDI, first argument register. And the bit layout of that register will have some bits devoted to the first field, some bits devoted to the second field, some bits devoted to the third field. And you'll need to make use of some assembly instructions to shift and mask so that you can extract each of these fields in its own way. It's a different syntax than when you have a pointer to a struct, because the struct is no longer in main memory, it's in a register instead. Now, I mentioned this here because A, it's important that you don't mix those two up, and B, to encourage you, if you're watching this before Lab 7, or watching it and haven't done Lab 7 yet, do Lab 7, because the entire point of that lab is to demonstrate techniques associated with those two things, a pointer to a struct and how you access those things in assembly, and a packed struct and how you access the fields of it in assembly. In addition to that, then there's some notes about, oh, here's what you might want to do with that data section. Remember, in most folks' cases, you had a set of bit patterns to say, oh, this is how you draw 1, and this is how you draw 3, and this is how you draw 9. And to that end, having those in an array was tremendously convenient, because if you determine this middle digit is a 2, then you go to array index 2, fish out some bit pattern, or it onto some stuff, and voila, you are going to display it a 2 eventually. Now, the setup for that to work in assembly is a little bit more complex. Usually the approach is to load up the address of this array into a register. Syntax for that is given here, making use of a leak instruction, something we'll talk about in lecture soon or have already talked about. I think that's set for the Wednesday, October 19th lecture to discuss the leak instruction. In addition to that, then, you'll want to be aware of the three-part syntax addressing mode in assembly that allows you to treat this R8 as over the beginning of an array, access some index, and then scale that index by the size of elements, in this case, ints in here. As you would use other things like shorts or bytes or longs up here, then you have to use a different scaling factor over here. But this is typically how arrays show up, if that, as they would show up in C, would show up in assembly down here. All right, so I think that's about all I need to say so far in terms of setup. There are, again, also notes on the third function, which is down here, bat update. It has its own quirks that, for instance, you'll need to play around with the stack by extending it, making space for local variables, passing pointers to those local variables, and so forth. But there are a bunch of notes about that, which are worth reading and following in terms of instructions. For now, I think it is worthwhile to move on to the second problem, which is this binary bomb business. There are a couple of things that are a little bit weird about this one. It's going to be a debugging exercise again, so you'll be making extensive use of GDB. Might be a good idea to review the GDB guide that is up over here. And I see now the link is wrong for this, so I'll correct that shortly. The other thing is you actually just need to get this bomb thing, and if you look in the source code that's provided, there isn't anything in there, although there is a suspicious script called bombdownload.sh. Now, importantly, this bomb business is functioning behind the computer science firewall, and so you'll need to be on certain lab machines in order to access some of the resources associated with it. In particular, if you want to download a bomb from a website, you might click on this thing and find it's just going to time out and never get anywhere. But if you were sitting at a lab machine in person, for instance, Keller 4250 or Keller 1250 in a lab, then this link would work because you'll be behind the firewall at the university. There's also Scoreboard that allow you to keep track of how far you've gotten on that, which is also accessible there. We'll have a look at that in a second. But probably the easiest way to get a bomb is to run the script that's provided when you're on one of the lab machines. And so I will, over here, fire up a terminal and log into Atlas. Human.edu. And I, being the smart cookie I am, implemented that SSH key-based authentication, which means as long as this thing goes through, I won't have to type a password or do authenticate. Super useful. Let's see. I need to get the source code for this thing. So let me make it a P3, and I'll change it to this thing. Now, if you're working on your whole project already on Alice, then you probably have your P3 code there already, if not needed. Let's see, now let me just come back over and I will grab this link once more, copy a link address, do a wget, unzip that thing here, I'll train into P3 code, and I'll see there's this bombdownload.shell. Just want to check to make sure if that has the right permissions on it. It is executable for me. In the event that you would run this thing, it says, permission denied, like not executable or something like that. You could do a little change mod u+x on bomb download .shell, but that did nothing right now because it's already executable. If I run bomb download .shell, then it will fetch a bomb for me, and great, the server must be down right now. All right, hang on a second. I'm going to pause for a second and figure out why this isn't working. Well, it looks like I just had to try a couple times here in order to get this thing to pop out. So on a second run of bomb download.shell, I got my bomb almost right away. Let's maybe get one third one just to make sure all is well. Now, you're welcome to download as many bombs as you want. The trouble with this is that if you download more than one, then you can only sort of get the maximum score of whatever the 5 or 10 or 20 bombs you have is. And if you happen to incur any penalties through explosions, then those will all count against you cumulatively. So in most cases, it's probably worthwhile just to get a single bomb here. You can have, see, I have a couple of these sitting around right now. I'll work on bomb 11 here by unzipping it. 11.zip. And if I change over into this bomb 11 and have a look here, then there'll be a few things to observe. There's a bomb.c, there's a readme, and then there's a bomb. If you look at the file types for each of these, you'll see bomb is actually just a plain old executable. Bomb.c is a C source, and the readme is ASCII text. Let's have a look at the readme. This is bomb 11. It belongs to Kaufman at UMaine.edu. Okay, not much to do there. Let's maybe have a look at the bomb.c source code. And as you would sort of plop your way through this, there's a main, very useful to know about. There's a mention of phases here, and that particular structure should be familiar because it's the same one that was used by Puzzlebox, where there's a series of phases. Phase 1, Phase 2, Phase 3, cool. The farther I get like more points. That's great. And so you look around and you're like, okay, where's the code for the phases? And this is where things get a little bit tricky. The code for the phases is missing. That in fact, it's encoded in the binary, but not in any of the source code. So you have to learn how to make use of GDB in order to diagnose the disassembled assembly that's present in that assembly. Now, it's the case that this bomb is going to accept an input file just as the Puzzlebox did. For instance, if I just ran this thing right now, if I ran the bomb, then you'll see, oh, this is sort of intimidating and like not that great to look at. If you type some stuff at this point and press enter, then it'll be accepted as inputs, but that might cause an explosion if it's the wrong input. So at this point, I'm just going to chicken out and press Control-3, which usually kills things. And there are just a few scare tactics in here that there wasn't actually an explosion here, but I'm just outside of the program at this point. Okay, so the right way to approach this is to fire it up in GDB and probably also to have an input text file of some kind. So let me just use nano quickly to work on this input.txt. I'll just write a hello world in here, save that, and suspend this for a moment by pressing Control-Z. And as the message indicates, I could press FG to return back to nano as I'm editing there. But instead, I'm actually going to fire up GDB on the bomb. And so here's GDB bomb. I'll probably put this in TUI mode as I did before. Press enter once. And here's some of the source code. It's the stuff that was in that bomb.c, but again, there's no phase stuff here. It'd be a good idea to set a breakpoint right away so I don't run too far here in this phase 1, for instance. Before I do that, I'm going to set my args to be that input.txt. And here's a trick that you're all going to want to employ at some point. I'll explain it in a little bit more detail later. Set a breakpoint, break at the routine explode bomb. This is the one that will trigger in the event that you get wrong inputs and end up about to explode the bomb, which will contact the server, note the explosion, and lose you some bonus credits for coming away scot-free without ever blowing anything up here. So explosions lose you a little bit of credits. More phases you pass, the more credit you get. The credit is bonus credit though, so if you exhaust all your explosions, then you still get 100%. It's just that you'll lose out on some of the makeup credit associated with no explosions. But setting this breakpoint here means even if I do something dumb like, oh, I'm going to run now, and there are no other breakpoints, so I'm going to run right through. That hello world is going to come out of input.txt and probably not match what the input is, but that's okay. Because I've got a breakpoint here at explode bomb. I'm saved and can rerun instead. Again, screen tearing here, so I'll press L, and this is the irritating part, no source code available. The only thing that's present here is the binary, but we'll disassemble that shortly. Right. What I probably want to do instead is to break at phase, and I will use a little tab collisions. I always forget it's phase _1 here. And that will allow me to see what's going on within that phase. So I've given this a run one more time from the beginning. All's well. Hit breakpoint 2, phase 1. Still no source code available, but that's okay let me change the layout and ask GDB, please show me the disassembled assembly code. And here, we actually have some source code. This is a set of assembly instructions that comprise what phase 1 is doing. You can see the assembly instructions look a little different than what we'll write by hand because, for instance, a lot of the suffixes are gone. What was a sub Q is now just a sub. What was a leak is now an LEA. And to that end, this thing looks a little bit different because there's not complete tool agreement about how those assembly instructions should be displayed, but it shouldn't be too hard to sort of interpret there. Now at this stage, I can start executing instructions like a step instruction, or SI for short, which will move ahead an individual instruction here. It's somewhat important that you use these SI, or next I instruction variants in GDB that move single assembly instructions forwards. Because if I just did a step or S, then it might try to interpret a sequence of assembly instructions as a line of C code and do several at once, which is no good. I really just want to go one assembly instruction at a time in here. So I'll do a couple of SIs here. And then maybe I don't necessarily want to go into this strings not equal function yet. So I'll use an NI to sort of step over it. See, there's this SIing business and blah, blah, blah. And oh crap. Okay, this is where I'm about to call explode bomb. So clearly something went wrong in here that I'm going to want to inspect a little bit more detail. All right, so that's cool. Maybe I'll rerun again and take a little bit more careful look at things here. As we discussed in lecture, it's possible to get yet more information here by inspecting what's happening in the register file. So I'll add the layout registers to this so that I can see what the registers are up here. And then proceed to, for instance, step through. And you'll see, for instance, as I call this sub instruction on RSP, the stack pointer, its value changes. Was 8 bigger, and now is 8 lower over here. And as I call this LEA, load effective address, that does something and plops stuff down in RSI over here, do a step instruction, you can see RSI changes to this very big number over here. Now I'm about to call a function, strings not equal here. And the bomb is tricky, but it's not so tricky as to say that this function is something different than what the name implies, that it's going to check if a couple strings are equal. And so it's not sort of worth your time necessarily to investigate those things too deeply, at least at this stage. Instead, I might get a little bit curious to know, well, what arguments are being passed to this function? And for that, you'll have to recall some conventions that we're learning in assembly. It's well, where do arguments for assembly functions go? Oftentimes, the lead up to a function like this one will populate certain special registers that are used to pass arguments in them. And we need look no further than one instruction above where RSI has its value set here. Looking back over here at that handy dandy diagram, you'll see that RSI mentioned here is argument 2. So this will be the second argument that is being passed to this function. We'll get to the first argument in just a second, but one might start to wonder, well, what is this RSI business? If that's being set to be something, what is it as an argument? This thing doesn't look very much like a string, but you might try, for instance, printing out RSI, and then realize, oh yeah, to print out registers, you have to affix a little $sign to them like this, and say that's great. It's a really nice big number here, but that's not what I'm interested in. I might try printing in hex, but I've already seen the hex here. What I really want to look at this thing as is oh, maybe this is a pointer to some place in memory. In that case, I may wish to examine what's at the pointed to location. Now there are a couple ways to do this. One way would be to invoke some C-style syntax here to dereference this thing. So in this fashion. Oh, sorry, not the dollar, but the star to dereference. But I much prefer the GDB built-in commands like X, which is short for examine a memory location. Doing so over here is not particularly revealing, but you can see that, oh, this is the address that RSI holds up here, and this is the stuff that's at that location. Since I don't know what's at that location, I might have to search a little bit. This is showing in hexadecimal format. It might be more useful to say, oh, show it to me in decimal format. 5434 is not particularly useful, but there are some context clues like string's not equal, maybe it's a string. And so in that case, I'll say, hey, show it to me as a string. Now that looks more like something I sink my teeth into. Did you hear about the restaurant on the moon? Great food, no atmosphere. Ha 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 ha. Oh, dad jokes. At any rate, this looks like a promising prospect for something that might go into my input.txt file. Before we get too far down that line, let's get back to this being the second argument to the function, strings not equal. Where's the first argument? Now you look around, you see there isn't anything else in here that sets other registers. I mean, subtraction off of the stack pointer, that's kind of its own thing. So it'd be a good idea to look back at what arguments, what register is used for argument 1. It's RDI. You can see over here it's like not even set necessarily. And that is because, well, this function was called, and if it happened to have an argument that came in as RDI, then RDI has something in it and can be passed directly to strings not equal. Now we might check that just a little bit. This is within a function, phase 1 up here. You can actually, within GDB, move up and down stack frames here. So if I type the command up, this will get me back up into main here. Well, main was actually specified in that source layout. So if I change my format back to layout source, then you see, oh, this is where I am in the main file. And the input here is passed in as an argument, and that's a read line, which I guess might come from stuff that I have. So let me print out what input is. Oh, it's optimized out. That is fantastic. Okay, no matter. If we move back down in terms of our stack frames and go back into our layout as I haven't moved around at all. I'm still about to call this thing right here. But I can look at the registers here, layout regs, and you'll see RDI has another value in it that looks, reasonably suspiciously like something else. So let me examine as a string what's in RDI, and it's our good friend hello world that was read straight out of that input.txt file. Now I think all this stuff is feeling reasonably good in terms of okay, I know this is not what I want as I'd call strings not equal. They're probably going to prove not equal. So if I step sort of next instruction here, because I don't want to do the strings not equal, you'll see this RAX comes back as a 1. There's going to be a test of 1 against itself. The jump, if it's not equal to 29, and that's I think gonna end up being a no good. So again, if we do this stuff, we end up down here. So apparently this strings not equal returns a 1 in the event that the strings were not equal, and perhaps it will turn a 0 otherwise, but if they are equal. So let's make them equal. I can one more time print out what's in RDI. Sorry, examine as a string what's in RDI. Oh crap, what happened? Oh yeah, I called a function. I actually called, this could have done anything, and RDI is actually one of those caller save registers, and the value that's passed in here, then RDI is not expected necessarily to be the same thing once the function is finished. So somewhere in my history, I have that thing, but I might have to rerun here to get back at that thing. So finally then, let's do some stepping here. Print out or examine what's at RSI. It's this string, so I'm going to make a copy of this thing. Copy. Now here again is a trick. I don't want to exit my debugging session because I have things set up actually pretty nicely, but I can suspend it by pressing Control-Z. That will suspend it, and if I look at the jobs I have on hand, got my editor here for input.txt, my GDB down here. So let me bring back into the foreground job number 1, which is my nano. I will paste in here that string that was over there. Get rid of my hello world. Maybe put it down here instead to see maybe that'll be input to the next stuff. Save this thing. I'll suspend it one more time. Bring back up job 2, which is GDB, and then I will rerun this time. Hoping for better input. A little screen tearing. I'll press Control-L to fix that. Move forward here now. So let's just check once here. What's at RSI's location? That's the thing that's over here. What's at our DI's location? Did you hear about the rest of it? Cool. Okay, so these two things match. And if I next instruction here to go over the strings not equal, lo and behold, I got a 0 back, indicating they were not equal, so they were equal. Now, control flow wise, this should take me someplace else as a step in instruction. Let's see, step in instruction. So I didn't jump down here to the bomb. I'm about to return from this function, and voila, we're in good shape. So there is our first phase solved. Now, it required a number of things. First, the ability to manipulate GDB in such a way as to actually look at those assembly instructions, knowledge of what goes into the register file, knowledge of some GDB commands to examine memory locations, and also then knowledge of the assembly conventions for where arguments come. And the common tactic is going to be, where is my argument coming from my input.txt coming into this function, and how is it being used? And then as well, looking at other things that are coming up in those functions. This is sort of the fun of things, but at this stage I might be a little bit curious about whether or not the sort of my passing of that phase has been registered. For that, let me log quickly into Vol. Let's see, Vol UMN. Just come over here, the virtual online learning environment. This is probably the fastest way to do it. Now again, this is a fully featured graphical environment, so it's overkill for working on the bomb, but in order to see the scoreboard, that's served through a web server, and the only janky way we know how to do it is to run it on their lab machines behind the firewall, so you have to sort of log in here to see it. Let me do authenticate this thing. Accept. Here, that's cool. I'll launch a session with XFCE. And then I'll need to fire up a little browser here. Firefox always takes a second to get online here. One thing I'll do in the meantime is to grab this link, one of the quick links here. So this is the scoreboard over here. Copy that. Copy as is. And this is one of those older fastXs, so it's going to be slightly irritating. I don't know if I can, I can't even paste here. There's a trick on the old fastXs, if like Control V or right-clicking and pasting doesn't work, then you can actually like paste into this stupid little clipboard thing here, and then send to remote. And now there should be something populated in terms of the clipboard. Not very ergonomic, but the newer fastXs on a lot of the lab machines, not Vol, but a lot of the lab machines, for direct login, that actually honors Control V and Control C and so forth. All right, well, it looks like this thing hasn't updated quite yet, but it should soon. And at that point, I should see some points on here for bomb 11, which is the one I was working on there. And to that end, that's all that needs to happen. So I think that's about all I have to say about the bomb stuff. The phases get progressively more difficult and take a little bit more effort, but the first couple are not bad to bang out. The scoring scheme for passing phases and making progress is listed down here in a little table. 10 points for the first 3 phases, 5 points for 4 and 5, 5 points for the 6th phase, that's makeup credit, and if you avoid any explosions, then there's a 5 additional for this. Every time you explode, you'll lose half of a point, rounded down. So there's a little table down here for based on number of explosions and phases, if you defuse, what your total points will be. One other note, the bomb itself needs to talk to the servers, so it will only run on certain machines, like Apollo and Atlas and the Vol machines and so forth. Over here, if I were on my personal desktop machine, for instance, let's see, I'm looking for here, yeah, and try to do something with I couldn't even download the bomb, but if I ran the bomb here, then I'm likely to get one of these sort of illegal hosts businesses. And so you'll need to run this on the lab machines in order to be able to get credit for it. And then check back after a while to make sure that things show up in the scoreboard for you. Whatever score shows up there is what we will eventually give away to you. It looks like someone, probably me actually, has already diffused a little bit over there. All right, that's what I have for you for the moment. As you have questions, come by office hours or ask in lecture. Happy hacking all.